When we have a buffer, we have a conjugate acid in solution with water to form the conjugate base and H3O+. In these buffer solutions, we have a significant amount of the conjugate acid and a significant amount of the conjugate base. And so if we're thinking about an ice chart, we start with some initial concentration of the conjugate acid and some initial concentration of the conjugate base, and we don't have any of this to start with. So to get to equilibrium, we're going to have to make the H3O+, we're going to have to lose some of the conjugate base, gain some of the conjugate base, and lose some of the conjugate acid. So at equilibrium, we're going to have conjugate acid minus X, how much conjugate base we started with plus X, and X of H3O+. Buffers are always made with weak acids, so we have Ka is small, and that means that X will be a small number. So we can always, in our buffer solutions, ignore X relative to our initial concentrations. And so in a buffer solution, we can write that our Ka is equal to X, which is the H3O+ concentration, times the initial concentration of conjugate base divided by the initial concentration of conjugate acid. And I can use the initial concentrations of conjugate acid and conjugate base here only because I start with significant amounts of those so that I can ignore X relative to both of these concentrations. So this trick is not going to work if I don't have some conjugate acid and some conjugate base to start with, i.e. if I don't have a buffer solution. Now, if we think about how we're going to solve this equation to find the pH, we know that eventually we are going to want minus the log of the H3O+ concentration. So let's take minus the log of both sides of this equation. So minus the log of the Ka is equal to minus the log of the H3O+ concentration times the concentration of the conjugate base divided by the concentration of the conjugate acid. So I've written it this way on purpose because I'm going to isolate minus the log of the H3O+ concentration so that I have pH. Now remember that the log of one thing times another thing is equal to the log of the first thing plus the log of the second thing. And so I can rewrite this as minus the log of Ka is equal to minus the log of H3O+ plus the log of the ratio of the conjugate base concentration to the conjugate acid concentration. Minus the log of the Ka is the pKa, so I have pKa is equal to, distribute the minus sign, minus the log of the H3O+ concentration, that's just the pH, and then I have to continue to distribute the minus sign, and so I have minus the log of the conjugate base concentration divided by the conjugate acid concentration. So now if I take this term and add it to both sides of the equation, I will have an equation for the pH of my buffer that depends on the pKa of the acid that I'm using and the initial concentrations of conjugate base and conjugate acid in my solution. So finally, I have pH is equal to pKa plus the log of the conjugate base concentration divided by the conjugate acid concentration. This equation can come in very handy because it is already solved. So we've taken the expression for Ka and just solved for pH. And so we've done all the work of our ice table and plugging into our Ka expression and solving for the H3O plus concentration and then taking minus the log to find the pH. That's all done in this equation. And this equation is often called the Henderson Hasselbach equation. And you can use this equation to solve for the pH of a buffer solution, or alternatively, if you know the pH of your buffer solution and you know the pKa of your acid, you can solve for the ratio of conjugate base to conjugate acid that must be present in that solution. And just one word of warning, you should only use this equation when you have a buffer solution. So if you do not have initial concentrations of conjugate acid and conjugate base, you cannot use this equation because we've made the assumption that we can ignore X relative to both of those initial concentrations. Let's practice using this equation by solving for the pH of an acetic acid buffer solution that contains 0.1 molar acetic acid and 0.75 molar sodium acetate. So the first thing to recognize is that acetic acid, which is CH3COOH, when it reacts with water, will form acetate, which is the conjugate base of the acetic acid, and H3O+. I'm going to need to know a pKa for this acid, and so if I look up the pKa, I find that it is 4.74. Note that the sodium acetate is just the sodium salt of this acetate anion. And so when I put sodium acetate, which is an ionic compound, in water, I will form this acetate anion. And so the concentration of sodium acetate is equal to the concentration of the acetate anion in solution. And so I have 0.1 molar of this and 0.75 molar of this. And I know that the pH is going to be equal to the pKa plus the log of the conjugate base concentration, so 0.75 molar, divided by the conjugate acid concentration, 0.1 molar. And I find that if I solve this equation, that my pH will be 5.62. It makes sense that this pH is more basic, larger, than the pKa because I have more base than conjugate acid in my solution. Now it's your turn to calculate the pH of a buffer solution containing ammonium chloride and ammonia. The ammonium chloride concentration is 0.1 molar and the ammonia concentration is 0.075 molar. Just as a hint, you will find the pKb of ammonia, but you will not find the pKa of ammonium chloride. Use the pKb to find the pKa. When you do this properly, you will find that the pH of this solution is equal to 9.14.